Good morning, everyone. So, today we are going to start a new topic, and the topic is differentiability. Okay, chapter 7. Now, before we proceed to understand the conditions that when do we say that a function is differentiable at a given point, let us try to understand what do we mean by differentiability at a point, okay, using graph. So here you can see that I have taken a function f whose domain is closed interval -1 to 1 and its codomain means range is subset of real numbers, and the function is defined as fx equal to x square. Now here you can see that this is a real valued function, and now let's say I want to check whether this function is differentiable at x equal to 1 or not. Okay, I want to check whether this function is differentiable at x equal to 1 or not. So what do we mean by that? By this we mean that whether we are able to draw a unique tangent at x equal to 1 or not. Okay, like here x is 1, so corresponding to 1 you can see on graph this is the point. Okay, so the question is whether you are able to draw a tangent, a unique tangent, okay, at this point or not. Clear? If you are able to draw a unique tangent corresponding to x equal to 1, okay, then we say that this function is differentiable at x equal to 1, okay, and we say that f dash 1 exists. Okay, now see over here. Here you can see that same graph, okay, same function. So I want to check whether this is differentiable at x equal to 1 or not. So this is x equal to 1, okay. So corresponding to this image is this, okay. So at this you can see that we are able to draw a unique tangent. You cannot have any other tangent than this, okay. So whenever you are asked to show whether the function is differentiable at a particular point or not, that means you are trying to say whether you are able to draw a tangent, unique tangent or not. Okay, if you are able to draw a unique tangent at that point, then yes, it is differentiable at that point, otherwise it is not differentiable. Now like here f dash 1 exists means it is differentiable at 1 and this value comes 2. Now what is this value 2? Okay, so this value 2 is nothing but the slope of that tangent, okay, slope of the tangent, that unique tangent which will be drawn at x equal to 1, okay, for x equal to 1. So last year we had only done differentiation, we were not talking about checking about the differentiability, okay. So like here f of x is given to be x square, okay. So we used to write like this, y is equal to x square, then we used to differentiate, yes, so we used to get 2x, clear. And then whenever you are asked to find the value of dy upon dx at x equal to 1, so in that case what you used to do, you simply used to substitute replace this x by 1, okay. So in that case we used to write like this, dy upon dx, and like this, x equal to 1, and then you will get 2 into 1, that is 2. So this dy upon dx at x equal to 1 was nothing but the slope of that tangent, okay, drawn for x equal to 1, clear. So dy upon dx at x equal to 1, sometime we write like this or sometime we write like this, f dash 1, okay. So you should always remember that whenever we are talking about differentiability of a function at a given point, that means we are trying to find out whether we are able to draw a unique tangent or not. Okay, so let us see few more graphs. Okay, then we'll proceed to the conditions, because all the time it's not possible for you to draw the graph and then determine whether the given function is differentiable at that point or not. Okay, like here you can see that uh, I have taken one function f of x is equal to 2 times x to the power 3 by 2. Okay, this is the function, and this is the graph of this function. Now if you see, if you want to draw tangent at any point, okay, like at these points you can easily draw tangent, and that would be unique tangent that you can draw. Okay, but when you want to draw a tangent at this point, okay, this is the end point, okay, this is 0. So if you want to draw tangent for this x equal to 0, then you observe that you can have so many tangents. Okay, like you can have this x-axis, or you can have something like this, or something like tangent means a line which touches a single point. Okay, so here point is 0, clear. For x equal to 0, image is also 0. Okay, so here you can see that you can draw so many tangents, so you are not getting unique tangent for x equal to 0. Therefore we will say that this function is not differentiable at x equal to 0. Okay, otherwise you can see that if you want to see whether it's differentiable for this point or not, then you can see you are able to draw a unique tangent. Okay, so here you can see that for this point you can have so many tangents. Okay, so you are not getting unique tangent, so therefore this is not differentiable at x equal to 0. It's not differentiable. Clear? So all the time it's not possible for you and me to draw graph and then just look at the graph and say that whether it is differentiable at that point or not. So we should have some method to find. Yes, so that method we are going to discuss later on. First let us see few more. Okay, few more graphs. Okay, see this. Here you can see I have taken, let me reduce this size. Okay, okay, now it's visible. So see over here, this is one function. Here this is called piecewise function. Okay, because you can see for x less than 1 or equal to 1, it is defined x cube minus 1, and for x greater than 1 it is defined as 3x square minus 3. Okay, so this type of function is called piecewise function. Okay, for certain values, for certain values of x you are defining differently, and for rest you are defining it differently. So this is called piecewise function, and now we have to check whether this is differentiable at x equal to 1 or not. Okay, so you can see over here, for x equal to 1, image is here only. Okay, so are we able to draw tangent? So if you look at this graph, okay, you will say yes sir, it's possible to draw tangent and we'll have unique tangent, but it's not possible to draw a unique tangent. The reason is this curve is not smooth. Okay, this curve is not smooth. It's till here it is smooth. Okay, and after that you'll find that it is going like this, something straight line is going. Okay, straight line is going. So that means at this point, no, you are getting something like this. Let me draw over here. Your smooth curve is there, and then all of a sudden it's becoming like this, something like this. Okay, not this much, but like this, and okay, so something like this. It's not smooth over here. At this point it's not smooth, so that means you are getting something like this. Okay, peak type. Okay, so at here you can see that you can have so many tangents. You can draw like this, or you can just tilt little bit, still you are able to get tangent, or you can tilt like this. Yes, still you are able to get tangent. So this is the reason why we are not able to get a unique tangent for x equal to 1. Therefore this is not differentiable at x equal to 1. Okay, for the rest rest of the points it is differentiable, because here also you can see you are getting a smooth curve. Okay, so nicely you can have a unique tangent. Here also you can have a unique tangent, but at this point where you are getting a peak type. Okay, so here you can see you can draw like this, you can draw like this, you can draw like this. So you are getting so many tangents, you are not getting a unique tangent. So this is not differentiable at x equal to 1. Okay, see next. Here you can see this is function f of x equal to mod x. Okay, this is the graph. Now if I ask you, is it differentiable at 0.1 sorry 0.2, this is 0.2, is it differentiable at 0.2? So you will say yes sir, at 0.2 it is differentiable because we'll get a unique tangent. Okay, but at this we are not getting unique tangent. We can have like this, we can have like this. Okay, we can have like this. Clear? So we are not getting unique tangent. So this is not differentiable at x equal to 0. Clear? So all the time, as I said, all the time it's not possible for you to draw the graph and then decide whether this is differentiable at the given point or not. So we should have a method. Okay, so where we can simply do little bit of calculation and we can say that yes, it is differentiable or not differentiable. So now we are going to discuss about that method. Okay. Okay children, now let us see the method, or you can say the conditions which are required for checking the differentiability. Okay, so see over here, a real valued function f of x is differentiable at any fixed point x equal to a if and only if the following conditions are satisfied. Now let us see what are those conditions. So the first one is left hand derivative which we will denote as capital L left hand, and derivative by this, okay, derivative of function at a will be denoted by this, yes, and this will be equal to limit h tends to 0. Since we are checking for left hand, okay, sorry, left hand, since we are checking for left hand, so that's why minus sign. Okay, and then here you will write f of a minus h minus f of a upon minus h exist finitely this is the first condition. Now second condition, right hand derivative r f dash a limit h tends to 0 plus will put because we are finding right hand. Okay, so f of a plus h minus f of a upon h exists finitely, and the third condition is that both right hand and left hand derivative should be equal. That right hand derivative should be equal to left hand derivative. Okay, so we'll say that a function is differentiable at x equal to a, okay, only if all these three are satisfied. If any one of this is not satisfied, then we say that it is not differentiable at that point. Okay, okay, next you write note the common value of right hand derivative and left hand derivative is denoted by f dash a, and it is known as the derivative of fx at x equal to a. Okay, so this note number 1 or note number 2. If however the right hand derivative is not equal to left hand derivative, we say that fx is not differentiable, is not differentiable at x equal to a. Okay, and number 3 you can write in each case h that we have taken in limit, yes, h is taken as positive and very small and very small. Okay, okay children, now before we proceed to questions, one more thing we are left to write, and that is relation between continuity and differentiability. Okay, so write down this relation between continuity and differentiability. Okay, so what is the relation between continuity and differentiability? So write every differentiable function is continuous. Okay, so every differentiable, once you come to know that that function is differentiable in given interval, okay, then you can say that that has to be continuous. So every differential function is continuous, but every continuous function need not be differentiable. So if you have a differential function in a given interval, then obviously that is going to be continuous. But if you have a continuous function, that may be differentiable or may not be differentiable. Okay, like here when we, okay, see this function f of x equal to mod x. This is the graph. Can you see this is continuous? Once I start drawing it, I don't have to lift my pen. Yes, so there is continuity. There is continuity. This is continuous function. But is it differentiable? No. See, if I talk about this interval -1 to 1 interval, you can see that at this point, at 0, at x equal to 0, this is not differentiable. That's why it's saying that continuous function, okay, every continuous function need not be differentiable. Okay, so you saw this example, yes, that this is continuous but not differentiable. Okay, like here you can see this, okay, this function, this is differentiable in this interval -3 to 3. If you consider this interval, okay, -3, here I have to change this, okay, minus, oh, it was correct only, no problem. So see here, if I see from the interval -3 to 3, okay, you just see it is continuous and it is differentiable. Okay, so what do you observe? That if the function is differentiable in a given interval, then that function has to be continuous in that interval. Okay, but if it is continuous in that interval, did not be differentiable. Like in this example, this was continuous in this interval, okay, but it was not differentiable. Clear? But if a function is differentiable, then that has to be continuous in that given interval. Clear? So this is important. Okay. Okay, now let us see questions. So here from exercise 7.1, question number 1, show that the function f of x equal to x square is differentiable at x equal to 1, and hence prove that f dash 1 means derivative at 1 is equal to 2. Okay, so see, given f of x is equal to x square and the given point is x equal to 1. Okay, now in order to show that whether this is differentiable at x equal to 1 or not, we have to find the left hand derivative. See over here, we have to find the left hand derivative, we have to find the right hand derivative, and if it happens that both right hand derivative and left hand derivative are equal, then we say that it is derivative. Okay, and that value that we get, that common value, that is only the derivative at 1. Okay, so see this. Now left hand derivative, so we are checking at 1, so we'll write 1 over here, and then limit h tends to 0 from left hand side, so minus, and then f of, here we'll write 1 minus h minus f of 1 upon minus h. Okay, now your function is defined like this, that if you have x over here, then image will be x square. So limit h tends to this. Now f of 1 minus h, okay, so you know that if you have x over here, then what you get as image? X square. So here your image will be 1 minus h whole square, and for here 1 square, and here simply minus h. Now limit, right now if you put h equal to 0, then you'll get 0 by 0. Okay, so firstly let me expand this. So using a minus b whole square formula, I get 1 minus 2h plus h square minus 1 upon minus h. Limit h tends to this. Here plus 1 minus 1 cancelled, 1 h will come out as common. Okay, or you can say write like this. First you can divide both the terms in the numerator by h. Yes, so limit, so you get minus 2 and plus here once again not minus, you will get 2 and here you will get minus h. Okay, now you put h equal to 0 and you will get 2. Okay, so left hand derivative is 2. Now we will find the right hand derivative. So next, right hand derivative at 1 will be limit h tends to 0 plus over here, then f of 1 plus h minus f of 1 and down only h. Okay, so from right hand side, so positive, so h. Now you get limit this, and here what do we get? Here we will get 1 plus h whole square minus, and here 1 square, here h. So you will get limit h tends to this 1 plus 2h plus h square minus 1 upon h. Then simplify and limit h tends to 0 plus, and here you will get 2h plus h square upon h. Limit h tends to this 2 plus h, you can put h equal to 0, you are getting a definite value, so that is 2. So here you can see that your left hand derivative and right hand derivative coming equal. Since right hand derivative at 1 is equal to left hand derivative at 1 equal, okay, therefore f of x is differentiable. It is differentiable at x equal to 1. Okay, and the common value of this one is said to be derivative at 1, and this is the answer. Okay, okay children, so this question is homework for you. Show that f of x equal to x to the power 4 by 3 is differentiable at x equal to 0, and hence find f dash 0. Okay, derivative at 0. So you have to do this. That means you have to find the left hand derivative, right hand derivative. If it happens to be equal, then it is differentiable, otherwise not differentiable. Okay, now let us see this question. Question number 2. Show that the function f of x is equal to 2 times x to the power 3 by 2 is not differentiable at x equal to 0. Okay, so let's see why it is not differentiable at x equal to 0. So solution, straight I am going to find the left hand derivative. Okay, so left hand derivative will be limit h tends to this f of 0 minus h minus f of 0 upon minus h. So here you can see that f of x is equal to 2 to the power this, sorry, 2 into x to the power this. So if you have x over here, then your image will be 2 times x to the power this. So in our case we have limit h tends to this, so f of this or straight, see 0 minus h will be minus h only, so we get 2 times minus h, and here 3 to the power 2 minus, and this will be 2 times 0 to the power this, so this will come 0 only. Okay, limit h tends to this, so 2 times this will be 0, no need to write here, minus h, we can write like this, to the power 1. Okay, this 2 is constant, it will come out, and here this base you can see minus h, so by the law of exponent we'll get minus h to the power 3 by 2 minus 1. Okay, so 2 times limit h tends to this 0, and here minus h to the power, here you will get half, so that means you are getting this. Okay, and you can see what we are going to get, 2 times limit h tends to this. Now this can be written as root h, okay, and here you can write I, yes or no, so you will get imaginary root. Okay, you are getting, sorry, imaginary, one second, we cannot do like that, so you just write like this. Okay, done. And for real this is not defined. Okay, not defined, straight you write does not exist, does not exist. Okay, so here this left hand derivative does not exist because here we are getting imaginary. Okay, and you know that for you don't have square root of negative number. Clear? And this is done, and then we will find the right hand derivative. Right hand derivative, limit h tends to this f of 0 plus h minus f of 0 upon h. So you will get limit h tends to this, and here you will get h 2 times h to the power this, here only 0, here h. So you get limit h tends to 0, here plus, and here you will get h to the power half. Okay, 2 is constant, it will come out, so limit h tends to this, and if you put h equal to 0 you will get 2 times 0, so this is coming 0, so this exists. Okay, exists, so you can write exist finitely. Okay, but for the left hand derivative, that left hand derivative does not exist. Okay, so here you can see that, so here we will write thus the left hand derivative does not exist, and therefore, or hence f of x equal to 2 times x to the power 3 by 2 is not differentiable at x equal to 0. Okay. Okay, now let us see the next question. Question number 4 says show that the function this is not differentiable at x equal to 1. Okay. So for that we have to find the left hand derivative, right hand derivative, and at the end we'll see that they are not equal, or maybe one of them not does not exist. Okay. So let's see. So left hand derivative at 1, limit h tends to this f of 1 minus h f of 1 upon minus h, limit h tends to this. Here you can see 1 minus h means this is less than 1. Yes. So if your x is less than 1, then we have to use this. So we get 1 minus h here cube, okay, and then minus 1. Clear? And for f of 1 we have this. Okay. So minus, we'll get 1 cube minus 1, and here we'll have minus h. So limit h tends to this, and here we can expand this part will be 0. Okay. So we'll get 1 minus h cube minus 1 into h, and here 1 minus h upon minus h. And sorry, this minus 1 will be also there for this one. Okay. And limit this, here plus 1 and minus 1 cancel, and thereafter this h will cancel. Okay. So you'll get h square here plus 1 minus h. So we'll get this much. If we put h equal to 0, then you'll get 1. Okay. Sorry, here we have made mistake. 1 cube minus h cube, here minus 3. Okay, minus 3h. So this will be, here it will be plus 3. Okay. So we'll get 3. Please correct this, because a minus b whole cube is given by a cube minus b cube minus 3ab a minus b. Okay. So here 3 was missing. Clear? So we got our left hand derivative at 1, that is 3. Now we have to find the right hand derivative. So limit h tends to this f of 1 plus h minus f of 1 upon h. So you have to see, for x greater than 1 it is defined by 3x square minus 3. So you'll get 3 times 1 plus h whole square minus 3, and for this we have to use this first one. Okay, x cube minus 1. So we'll get 0 for that. Okay, so straight I'll write 0, and here h. Now limit h tends to this. Now expand this part, so you get 3 can be taken out as common, so 3 comes out, and you are left with 1 plus 2h plus h square minus 1 upon h. So limit h tends to this 3, here plus 1 minus 1 cancel, then h will cancel, so you are left with 2 plus h. Now if you put h equal to 0, then we'll get 3 into 2, that is coming 6. So clearly your right hand derivative not equal to left hand derivative. Yes, therefore f of x is not differentiable at x equal to 1. So this is done, and this is all for today's class. Okay, one second, before we end this class, let me give you one homework. Okay, so these two are your homework, so you can just pause the video, okay, and you can write it down, and then you have to solve it by yourself. Okay, so these two questions are to be done same as what we did just now. Okay, you have to find left hand and right hand derivative, and you will see that they are not equal. Okay, so this is all for today. We'll have one more lecture on this. Okay, and then this topic will also get over.